you, Chairs. So now something a little bit, I guess that looks, okay, doesn't look good on here. A little bit different. What I'm going to talk about is sort of an opportunistic set of analyses we did, having heard about this workshop and realizing that as far as I knew in the literature, there hadn't been a really detailed study of the dynamics of motion on and about Phobos. So it seems like a great opportunity, and we actually teamed with Konrad Wilner and Scheeres to use the latest models that we have for the Phobos shape and from the literature for the Phobos environment in order to understand what what are the mechanics for exploration around this unique body. So, as I just said, the goal here was to provide an accurate description of the dynamical environment about Phobos, and we wanted to base it on the best available data. What do I mean by dynamical environment? And it really has much more of an exploration focus and context, although I'll pull in a little bit of science at the very end. So first of all, we're interested in how do you move across the surface of a body like this? And you need to describe the environment on the surface, such as traditional things like surface slopes. But there are also some other interesting limits, speed limits, if you will, about how you can move from point to point across a body in this somewhat exotic dynamical state. And we also looked a bit at orbits around the body, and with a specific focus on finding which sorts of orbits could be stable and useful from an exploration point of view. So that's sort of what I'll cover here. So for Phobos models, I'm just going to punt the description to Dr. Vilner's talk later on today, but we're using for most of our calculations the very accurate Phobos model that was developed recently, shape model up to degree and order of 45. Sometimes we convert this into a plate model. Sometimes we can actually directly use the spherical harmonic description of the shape model. We have, of course, the rotation period in that tidal gravity field. And for the density, we use, I guess, slightly old value of 1.87 from the Petzold et al. Paper. There are other interesting dynamical phenomena that happen at Phobos, but for the sorts of dynamical analysis we're looking at, these are not so significant. These include the Mars higher order gravity field, which has a very small effect, and deviations from synchronous rotation. It's estimated that there's about a 1 degree libration that goes along with the eccentricity. Again, that's so small that the dynamical effect of that for motion in this environment is quite small. So just to show a little math, why not? So here's Phobos. This is the frame we use. X-axis points towards Mars. Y-axis is in the against the motion of Phobos, and Z is the out of plane. And if you do a rigorous analysis, it's pretty easy to reduce the equations of motion to something pretty simple that really just depend on the mass distribution of Phobos. And this is taken into account that it's a highly non-spherical gravity field, and the effect of the tidal force of Mars, which really comes down to this very simple two terms here. From this, we can define what really motivates the rest of the discussion, which is the geopotential, which has this tidal term and then the mass term from the mass distribution of Phobos. We're assuming constant density, of course. And then you can actually write the equations of motion as well. So that's it for math for a couple slides. Once we have this geopotential, this really defines everything dynamical about Phobos and in this Phobos environment. And the first thing you can do is actually look at the surface geopotential. And this is defines really where down is and where up is. You know, what's the lowest point in the surface potential, which actually and naturally lies along the points of Phobos that point to Mars and away from Mars. This is the view looking from Mars, and this is a view looking down on Phobos. Mars is to the right, Phobos moves down in this frame. And there's actually a very interesting thing that pops out as soon as you look at the geopotential. We would expect the lowest point on, or sorry, the highest point on Phobos in this tidal gravity field to actually be at the north and south pole. Instead, we find it the lowest point to be at the trailing edge and the leading edge. And I've got a slide or two talking a little bit about that later on. We can also map the surface acceleration across the body. And here we do see that your local weight, if you will, would vary by at least a factor of almost 2, depending on if you were at the sub point or at the leading or trailing edge of the body. At this level of G, it's about less than 0.7 millig everywhere. You can actually do this comparison for lunar regolith properties and cohesion, and it does turn out to be on the order of millimeters, where the weight of regolith grain and the ideal cohesion of that, of 2 grains together, would equal each other. That sort of implies that when you get down to hundreds of microns in size, that these are and should act more like cohesive powders in this environment. We can also look at surface slopes. Here, these are calculations. Again, all these calculations that I'm showing were done by Mr. Stefan Van Waal, who has a poster talking about other exploration factors in this environment. The slopes across the body are actually quite relaxed, except for several distinct areas in the vicinity of Stickney Crater and other craters where they get up to 40, 45 degrees. Otherwise, the average slope is quite low. There's actually a very interesting study done by Dr. Scheeres that Dr. Vilner will maybe show a few slides on that I don't have time to cover here related to the slopes. So these are sort of the very direct applications of the geopotential. There are actually a lot of interesting dynamical phenomena that we can extract from this, which relates to how fast you can or would want to walk across the surface, what the outcome is if you happen to slip and fall on a banana peel, say, and interesting things like that. So the geopotential, as I mentioned, measures the potential energy in the rest frame of Phobos. And if we add a kinetic energy term to this, it actually defines an energy that we can use to define all aspects of motion in this body. And it actually gives us limits on speed that can be achieved under natural motion for a given level of geopotential energy. When we bring this into the Phobos environment, we actually get strict restrictions on motion across the surface. And we can have speed limits for maintaining contact with the surface. If you walk faster than a certain speed, you'll actually lift off into orbit. You can have speed limits to ensure that you will remain captured to the Phobos location and to the surface. And these can actually be factored into the design of mobile devices and operation strategies across Phobos. And that's really the driver for some of these analyses that we do. So let me just walk through a couple of these examples. The first one, what we call surface speed. This is, if you will, the maximum speed that you can attain if you just roll downhill in the Phobos environment. So the highest point in the geopotential, as I mentioned, is in the trailing edge of Phobos. Leading edge is also relatively high. And if you just took a marble at this point and you rolled it downhill, by the time it got down to the sub-Mars point, ignoring friction, which of course is important, you would actually get speeds up to 5 meters per second or so. So this is sort of an energetic way of thinking about how much energy you might gain as you jump from one point to another across Phobos. Another way of thinking of it is if you stood at this highest point and you jumped in the right way, you could land here at speeds up to 5 meters per second. So this is fine, but what's the relevance of this? Here we're actually mapping a slightly different concept, and this is the speed below which you need to have if you want to guarantee that you'll never leave the Phobos system. And what you see, these blue regions are actually speeds where if you just slip and fall, say, it's energetically possible for you to actually escape from Phobos and go into orbit around Mars. And that sort of makes sense. If you go back to the surface speeds calculation, if you slip and fall at this point, by the time you get to the lower point, you're going at over 5 meters per second. If you don't, dissipate energy with friction. If you look here, you only need 4 meters per second of speed to actually escape from the Phobos environment. So slipping and falling from anywhere of these blue regions actually can give you sufficient speed to escape from this region. So that's sort of an interesting aspect. Another interesting aspect with which Stefan has been working on and defining recently is just the concept of a speed limit across an arbitrary body to ensure that you stay on the body. In the low gravity field of Phobos or other rapidly rotating small bodies, if you actually walk too fast, the combination of the local curvature, the gravity, can actually give you enough centripetal acceleration so that you can achieve orbit, or you can basically walk off into orbit off the surface of this body. And it's a directional concept, because if you walk against the rotation rate, you actually can walk faster. If you actually walk in a concave region, you can walk as fast as you want. But if you round a hill, or if you round a crater, you actually have to be a little bit careful for your rover device or for the walking astronaut, unless you want to have a ballistic period, which you probably don't want. So here we've mapped over the minimum liftoff speed directions, and these are hang around about 3 to 5 meters per second, which is actually pretty nice, because walking speed is about 1 meter per second. So I think an astronaut would be pretty safe walking around Phobos. And then the maximum liftoff speed, and in some regions, you can go as fast as you want, and you don't have to worry about lifting off. We can also move off of the surface. Here's a plot of the two equilibria that exist for Phobos. And we've also done an analysis of orbital motion in the vicinity of Phobos. And we looked at a wide range of orbits. There's really only one class of orbit that is very safe for motion around Phobos. And these are these distant retrograde orbits that come all the way down, but they're actually very stable all the way down till where they skim the surface. And I think my time is running out, so I'll just show this. And it's actually, again, a very counterintuitive situation. As you get closer and closer to the surface of Phobos, the orbit period decreases, which is expected, but the speed relative to Phobos also decreases. So that orbit that skims is only about 11, 12 meters per second, which is still a relatively high speed. But that means that from that very close orbit, if you wanted to deploy something ballistically, you would have to have it be able to sustain impact speeds of definitely over 10 meters per second, which is about 50 miles per hour, which is pretty fast. Had a few other things about ejecta. I just want to point out that there's a very interesting feature, geometrical feature for Phobos on the trailing edge that actually makes sense in terms of the ejecta from Phobos. Maybe not from Stickney, that's kind of large, but all the smaller ejecta that goes about. But I'm not going to cover that. We've also analyzed Deimos in the past. But in summary, Phobos has a unique dynamical environment. And to explore this environment, it's crucial that we understand and explain it. And that's what we've been trying to do with this study. Thanks.
Actually, this is a shameless plug for a poster, but this is really interesting work, and we've taken a lot of this and looked at what happens in terms of ejecta from Stickney. And poster 4 looks at how the rolling and bouncing ejecta could in fact help to explain the grooves, including the lifting off and return of some of this. So it's a really, really great work. Thank you.
Hi, Dan, great talk. So this is an urban legend type question. Are there places on Phobos where you actually fall uphill? Can you fall out of a crater?
Well, uphill is always defined
Sure, I mean,
by the
topographically
geopotential.
up.
So, but if you think about it, the longest point of Phobos is actually along the x-axis that points to Mars. However, that's the lowest point of the body. So whenever you fall on Phobos, you are in some sense falling uphill because you're falling further and further from the center of the body.
Right.
So.
But, okay, otherwise no specific location where you would see something coming out of a crater, for example.
I think all the craters locally collect just because of the topography.
Yeah, exactly. Okay.
Okay, we'll have a discussion after. So I need to stick on the schedule. I'm sorry. So the last talk for before the break. This is by Dana Early, simulation